So when we're dealing with more complex pH and pOH problems, or power of hydronium and power of hydroxide problems, remember that concentration, and that's molar concentration in moles per liter, ionization, and pH/pOH are extremely interconnected. So when we're dealing with more complex problems, it's perhaps helpful to recall this designated pathway. And by the pathway, we mean to go from molar concentrations, or C equals N over V, where your N is moles and your V of solution is in liters, to ion stoichiometry with the hopes of getting H plus and OH minus ions. And then once we have the H plus or OH minus ions, we then plug in any one of these three formulas in order to get whatever the question is asking for. So let's use this pathway in order to solve more complex pH and pOH problems. So this problem reads, what's the pH of a 0.500 moles per liter solution of calcium hydroxide? So the first thing that we do according to the pathway is get the concentration, but we see that we actually have the concentration. So when I look at the first step of the pathway, I can just write concentration and then put a little check mark. Now, the second part is to develop an ionization equation in hopes of getting H plus or OH by this. So here's the ionization or dissociation of calcium hydroxide, and so it breaks down into calcium 2 plus and 2 moles of OH minus, and we begin this process with the listed concentration of calcium hydroxide, 0.500 moles per liter. And what we're going to do is use stoichiometry in order to get our hydroxide concentration. Using the 2-to-1 mole ratio between hydroxide ions and calcium hydroxide, we go 0.500 multiplied by 2 over 1. The hydroxides here would cancel out, and we'd finally be left with 1.00 moles per liter of course, hydroxide ions. Since we have hydroxide concentration, we're going to go from pOH to pH, initially finding the power of hydroxide using this formula here, a log base 10 formula, 1.00. And then once we have a pOH of 0, we're then going to use the combined formula of pH plus pOH equals 14 in order to isolate for the pH, which would then give us pH being equal to 14 minus 0 from over here. And we see that this solution finally has a pH of 14, and it being basic definitely makes a lot of sense. So our next problem reads, what is the pH of a 300 milliliter solution, so that would be the total volume, that has 2.5 milligrams of HI, or hydrogen iodide, dissolved in it? So the first thing that we're going to do is get the concentration of this solution. So to start this process, we're going to convert the milligrams to grams so that we can find our moles using our grams divided by the molar mass, or grams per mole formula, and we end up getting a molar amount of 0.000195444, which we're going to insert it right into here as follows. We then get a molarity of 0.006541 moles per liter, which then can now lead us to the second step, and that's developing your ionization equation. Here we have the ionization of hydroiodic acid now, or HI, and of course the interest in us developing this equation is to get our hydronium ion concentration over here. Using stoichiometry, that would give us the following. One thing we should mention is that the concentration that we found in the previous step was, of course, for HI over here. And so now using stoichiometry, we can see that it's a 1-to-1 mole ratio between H plus and HI. So these would cancel out, and to simplify, us having a concentration of 0.0000654 moles per liter, of course H plus concentration, which then allows us to move on to step 3. We're now going to take this H plus hydronium concentration, insert it into the H plus section of the pH formula, and plug it in, and we should get the following pH. This gives us a pH value of about 4.184, and considering that this is an acidic solution, it should be below 7, so it looks like what we have here does make sense. What I urge you to do is use this pathway to solve more of these types of problems. Go to the worksheet posted and email me if there are any questions.